Yeah, perfect.
Super duper. So, right, we'll crack into this. In general, I think, John, we've got your members are surveyors.
Surveyors, building control surveyors, consulting engineers, architects, students, a broad range of things. I'm a multidisciplinary engineer myself, building engineer, etc. So we've got a range of practitioners and students. I would think we've got people potentially coming in from our international chapters as well on today. That's the beauty of an online event like this. So thanks very much.
It is indeed. Thank you for that that update. That's brilliant. Well, what we're going to try and do today, guys, is get your minds thinking about the ground, the dark art of geotechnics. It's something that I've been involved with right from graduation, and then did a soil mechanics MSc, and I've always kept that side of it. So even though stress itself is really all about structural repairs, we've always kept our bent in the ground, and this is what we're going to talk about today. That's myself. I'm the co-inventor of the system we're going to talk about today. My colleague Simon Collis, who's a lovely chap and actually probably delivers better than I do, is my co-inventor. He's a materials engineer, and we came up with this rather weird and wonderful way of consolidating the ground. Just briefly, so that it sort of registers in your minds, the stress group comprises Stress UK, which is really what I'm talking through today, well, that hat on. And within that, we've got various different divisions. So Permeation Engineering is part of the Geotechnics division. We've got Heritage Engineering, which carries out lots of work to listed buildings, monuments, churches, and anything exotic that we can get our hands on. Structural repairs, we do everything from masonry reinforcement to stone repairs through to carbon fibre plate bonding and strengthening in those sorts of ways. It's a concrete repair too, generally putting buildings back together, because one of my sayings was when I started this company up 30 years ago, as soon as a building is finished or a structure, it's starting to fall apart, and therefore it will always need somebody to update it structurally, to alter it structurally, and to make repairs. Goldhawk, we've had since 2012 in the group. This specialises in masonry arches. So we repair everything from vaults under roads that you'll get all over the country, attached to houses and shops, right the way through to highways, bridges, and network rail bridges too. We repair and fix those. So Goldhawk fits very nicely in the group because it has all weird and wonderful specialties to it. Due Innovations, which links in today, is all about R&D, developing new systems in the ground, which Simon and I do. And if we get something that we know works really well, we patent it. So the product we're going to talk about today is actually patented. Right, so that's us. So I'm going to try and demystify polymer grout injection. And why would you actually want to grout inject the ground? Well, it's because we want to turn basically a loose soil into that. That is a lump of material that we have injected in the ground, and we happen to have collected through an excavation. I'll show you later just how we get that. But that's what we're trying to achieve. Okay, so we don't want to dig the ground up. We just want to inject it and create something really hard. We're going to tell you about the science behind that. We're going to tell you how we're sure it makes it works. Sure it works, because obviously we can point something in the ground and go, wow, we've injected that. That's it. Fine. How do you know? How can you rely on it? Are you going to put a building on it? So there's got to be a certain amount of surety, no smoke and mirrors. And I'm going to tell you about what types of soil it does not work in. Now, this is really, really important, because there are people out there at the moment pulling the wool over lots of quite important organisations' eyes. And it's so important that we get that message across today, what types of soil this does not work in. So that's what we're going to try and achieve today. So permeation ground engineering, what is the definition? We're going to mix two things together in the ground. One is a fluid that binds the particles together, and obviously the other thing is the soil, which is already in situ. And the reason to do that, so we strengthen the ground to give you better bearing capacity. Okay, simple as that. Or is it? So the task is therefore very simple. Deliver the grout or the fluid, whatever it is that you want to use, to where you want it in the quantity you want it. That's where the surety comes from. Not as easy as you would think, because all fluids don't behave the same. For a start, think about well, just water in your garden hose, or a balloon full of water, or a super soaker. Okay, that's water under pressure escaping, basically, and fluids will always escape to the point of lowest pressure. So garden hose, hole in it, squirts out because it's going to atmospheric pressure from probably about 3 bar. So remember that, keep that in your mind. It's all about fluids trying to escape to the lowest pressure, and you'll see why that's important in the techniques that we do. So we're going to compare two fluids to start with. Remember, we're going to try and get this fluid into the ground. A Newtonian fluid, you may not have heard that expression before, but basically that's gin, whiskey, water, petrol, oil, anything without any solids in it. A particulate fluid for those in the engineering world is like a cementitious grout or a bentonite. It's a suspension of particles which you then hope will create something of structural significance. So with cement, it hydrates, solidifies, and obviously encapsulates whatever it's with, be that an aggregate or whatever. But what we're going to do is show you now that they don't behave as you would expect them to do in the ground. So first of all, we've got a little experiment here. Demonstration 1 is a Newtonian fluid permeating, remember that word, permeating into the soil. So on the left, we've got a fine sand, and on the right, we've probably got the most permeable soil on the planet, sand and coarse gravel. Okay, let's see what happens when we pour in a Newtonian fluid. Okay, so this is what you would kind of expect to see if you did this. Nothing remarkable, but in your mind's eye, this is permeation. Watch how that fluid, under its own gravitational pull and particle attraction, is just pulling its way and soaking through the soil. Okay, so that's permeation. That's the whole principle of what we're trying to do here. We're not forcing any material in, we're allowing it to soak in. Watch what happens if we try and use a particulate fluid. So here we go, similar viscosity. Right, so there we are. Fine sand on the left, doesn't even go a millimeter into it. No tricks, I haven't put any cling film on the top of that. That's exactly what you will find will happen with a particulate fluid. I mean, even look at the most permeable soil on the planet on your right. It's only gone 50% of the way through. And the reason for that is that the little platelets get stuck between the particles of soil. And then the next platelet comes up behind it and jams behind that. And you create a filter. And the only way you're ever going to get a fluid into that soil is to increase the pressure. And you increase the pressure and increase the pressure, and it holds back, more particles jam up behind the next one, and then suddenly it'll break through. And what you create is called hydraulic fracture. You may have heard of that. And this is really pressure grouting. So what you're doing is you're forcing a fluid into the ground to actually compact it. Now that's fine if you're looking at massive volumes and you don't really worry too much about where it's going. But if you're doing a house and you're going to squirt some resin in, you want to know where it's gone. Hydraulic fracture will not give you surety of compaction of the ground. So particulate fluid. So if this is it, this is a demonstration of what we're trying to do. We're trying to get Portland cement in suspension into the soil. Goes so far, stops. Oh, by the way, what I was showing you there, that white fluid, that was microfine cement. That wasn't even ordinary Portland cement. That was microfine cement. So it will go a little bit further like that. If you use the Newtonian fluid, that's the pressure distance curve that you will get. It will just flow into the ground quite nicely. We're, however, going to use something that binds the soil and has another quality, which means it actually reacts with the water in the ground and actually gently expands. Not a big explosive reaction of a foam, which other contractors use. This is actually a hydroreactive resin, and it gently expands and pushes itself through the soil, doesn't move any soil particles, just pushes itself through the soil, then cures, stops, and creates that. You can see how hard that is. The only way you can tell, actually looking at that there's actually anything in it that shouldn't be there, is the smell. If you smell it, it's got a very slight sweet smell to it. Okay, so that's how you know it's got it in. Otherwise, you would never know. So if we inject that into the ground, it gathers the moisture. You can see it tailing off there naturally with the original pressure that was put in with. The mixing with water sets the reaction off, and microfine bubbles of CO2 are generated. I mean microfine, you can't see them, and they do two things. They gently expand the fluid and they reduce its viscosity, which means it travels through the soil even more easily than it did before. And then obviously it goes as far as it can, the reaction stops, it cures, and it creates a solid. So that's what we're trying to do. Sounds easy, isn't it? Stick a tube in the ground and pump some of our material in it. Wonderful. So why invent a new system to do that? Just use a pipe. Well, going back nearly 20 years now, I subcontracted some work out. Being a geotechnical engineer, I heard about this polymer injection, must try it. Found a job that was perfect for it, stabilizing a slab under a conservatory up in High Wycombe. So I thought I'd go along and see how they did it and find out all the magic about this. So I arrived on site. There was a technician there with a very smart truck, and I asked him what he was going to do. So he said, well, I'm going to drill holes at 1 meter centers in the slab, 25 mil diameter, and all around this. It was only a conservatory, small conservatory slab. Fill underneath it just needed settled, needed consolidating. And then I'm going to take this big long drill bit, about 1.5 meters long, and I'm going to drill down to 1.5 meters and sequentially go into each hole. I think about that. So he's taken a 25 mil drill bit and he's drilled down 1.5 meters into the ground. So what are you going to do now? And he said, well, I'm going to put a 15 mil copper pipe down into that hole, resin it into the slab, and then go and get a cup of tea. So he did that in all however many holes there were. And I said, what happens next? He said, well, when I come back, I'll bring the resin in the hoses, heated lines, and the gun, and then in each one in turn, I'll put the resin in and link it in. So I said, fine, great. How much resin do you put in each one? He said, oh, loads. So I said, what do you mean loads? He said, oh, we're told to put as much in as we can. So I said, oh, that's interesting. I'm the client. I didn't tell him that, by the way. I didn't tell him that I was the boss. I just said, I'm here to observe, really interested. I thought, well, it's going to be interesting to see what bill comes at the end of this, because he's going to put loads in the ground. Not as much as you need, just loads. Anyway, he'd done 3, and there was a knock at the door. And I went to the door because the client of the house wasn't in, and there was a very irate lady at the door. She was really, really disturbed. So she said, well, what, are you working here? So I said, yes, we are. We're doing some specialist work. And she said, well, I don't know what's happening, but I may be linked with you. Could you stop? So I told the technician to stop. I went next door with a lady, and I said, what's happening? She said, well, I was in the kitchen and I noticed that my washing machine was starting to move across the kitchen floor. So I went, really? Anyway, by the time we got into her kitchen, not only was that washing machine probably about 100 mil out from the units, but the wall tiling was cracking and the wall units were starting to move as well off the wall. So I said, come on, we better get out. So I reassured her that we'd put everything right. It's bound to be something to do with what we're doing next door. I said I didn't have a clue why at the moment, but I'd get to the bottom of it, inform her insurers. I'll get hold of our insurers and I'll make sure everything's all right. Anyway, so I went back next door, told the technician, you better pack up, something's gone wrong. Go home, report it to your insurers, and we better get a conversation going about how we fix this. So, geotechnical engineer, aren't I? I thought, what happened there? Why did that go wrong? Now go back and think about what I told you there. He drilled a 25mm diameter hole in the ground with a 1.5 meter drill bit. He then put inside it a 15mm copper pipe. The resin can only come out of the end of that pipe, so it's down at the bottom, out of the end. Where does a fluid under pressure go? Goes to the point of least pressure. Where's that? Straight up the side of his copper pipe, out under the slab, not where you want it in the ground. So I thought, well, there's interesting. How did it get next door? When we investigated, we found an old duct that nobody knew about. It must have been put there by the developer when he did the housing, maybe for a cable or something like that. It had got into this. It had shot sideways under next door, and there must have been a gap in the pipe or a hole in the pipe or something like that. It went straight up the cavity wall, the nearest cavity wall, detached house, and then started to expand. And it just pushed all the block work off on the inside. And of course, that took all the ladies' cabinets. It pushed a washing machine across the floor, etc., etc. That's why we needed to invent a new system, because that system is clearly used by this company. And by the way, they're still using it. Doesn't work. It doesn't give you any surety. You know, it's just not right. You can't force a foam into the ground. And by the way, that hole that he used with a 25mm drill bit wouldn't have stayed open unless there'd been clay in there. Because if it had been non-cohesive, you know, non-cohesive fill, rubble will have dropped in as he pulled the drill bit out and he wouldn't be able to get the copper pipe in. So lots of things wrong with that particular system. So here we go. Let's invent a way of delivering that resin. Now this looks good, doesn't it? Here we are. That is what actually one of our lances, steel. If you can see that, but good thick steel tube. You can belt that into the ground. Now, if we belt it into the ground, it means that the ground is actually tight around that. So there'll be far less ease for the resin to come up and go that way rather than just sideways. So we thought we'd nailed it. So we put these in the ground, we put a packer in the top, and we started pumping resin in. What do you think happened then? Well, if you think about it, where's the lowest pressure? Just up near the top. So of course all the resin pours out of here and you get virtually nothing coming out in this lower level because it's there's a higher pressure there. There's more effort for it to come out here, so it just pours out the top. So that isn't the answer. But if we put valves in, it's starting to get complicated now. But if we put valves in, here's a Blue Peter version that that we made before. We put valves at certain centers and we deliver the resin through a tube in the middle, then only where the tube is into that particular segment of the lance will the resin come out. So yeah, let's give that a go. So in fact, we did lots of experimentations with lots of different valves, because obviously you've got to make these things, they've got to be reliable. And this is what happens. So you fill that first chamber. Resin can't come out in the chamber above it because the delivery tube is blocking through the valve. So you only get resin coming out at that lower chamber, and you deliver it, and you continue the pumping until you've put the right amount in. Okay, and I'll come back to what is the right amount. You then pull the tube up into the next chamber. Valve shuts because it's spring-loaded neoprene, and then you start to fill that chamber, and so on. So you do that all the way to the top of the lance, and you've created something of about 0.5 meter diameter of consolidated ground. So let's repeat that and showing you what we would do if it was a domestic house or any sort of footing really. We've done it through concrete pads in all sorts of depths, but generally it's concrete or brick footings that we go through. So you dig a very shallow hole to expose the top of the footing, and you drill a 40mm diameter hole through the footing, be it concrete or brickwork. And then you drive these lances to whatever depth you've designed your underpinning to be. You join the next section on, and you drive. You drive to the design depth. The delivery tube is already in there, so we slide the tubes over, fit them, keep driving, keep driving, keep driving. The graphic shows that being fitted, but it's not. We then start pumping. So there again, we're going to repeat what we showed you before. And then you pull it up to the second injection level. The first injection level, you've started to get that chemical reaction going, and the resin then just starts to flow out further. So we've gone with the right amount of resin, we've gone 125mm from the lance. Not far. We want the resin to flow out about that far, just permeate through the ground. The chemical reaction will then take it to about 250. Okay, so that's both sides. So you've got a 0.5 meter diameter, approximately, consolidated ground. Quite boring, quite monotonous, particularly when there's a couple of hundred lances on a job. And there you've formed your pile. So that now is something really quite hard. I mean, you saw that again. That's the material that you've just created in the ground to help support your house. How do we drive these lances? Simple. With a road breaker. That's all it needs. We have driven to 27 meters on a slightly different job with a road breaker. In general, you're going less than 5 meters, probably more for 3, 2.5. But a road breaker will drive these very efficiently. And you can see that how little disturbance there is. So we're not underpinning. Just think about that. Well, there we are underpinning, but that is all the disturbance that we need to do to the ground to underpin that wall to 2.5 meters depth. And what does it look like when you dig it out? We've dug hundreds of these things out to see what they look like in various different types of soil. That's what it looks like. This is one of the early ones that we did. and very illustrative. You can see it's a rough shape. It's gone a little bit further. The resin has gone a little bit further into the a free draining gravel layer, which is fine. It's not a problem. We'll probably hear the pumps change tone slightly when they do that. But if we took a spade to that, it would ring. So exactly the same as you can hear this. And slop water everywhere. It is hard. How hard, I'll tell you in a minute, but it is solid. Okay, so you can drag it out the ground. So there we are. We've dragged one out of the ground using the lance to haul it back out. So that shows you just how well that material has bonded to that unprepared piece of steel lance. Steel stays in the ground. You cannot get it out for that reason there. So that gives you an idea roughly what you're creating. And if you were underpinning a house, you know, you'd put them in at around about 1.2 meter centers. Depending on the load you're trying to take, we've done pretty tall buildings with some high loads. You might bring the spacing down to a meter, but generally 1.2, and we have standard prices for doing that. So let's recap. You've got something about 0.5 meter diameter, up to 14 meters or more in length. It's not economically possible to do that. And occasionally, for whatever reason you do, you need to deliver the resin to that sort of depth, you can do it. Up to 800 kilonewton capacity. I mean, that's huge. 80 tons. We've extrapolated that from pile tests that we've done. We've actually never tested beyond just over 20 tons or just under 21 tons. But of course, you're not needing to create huge capacity piles. And remember, that's all done through a 40 millimeter diameter hole. What we do is we create a gasket at the top with foam and tape, so that when that's driven through the footing, you get a nice tight finish fitting on that, so that the resin then doesn't come up through the footing. And that works very well, very simple. So let's think about the advantages. For those who have a health and safety bent, you obviously don't need to excavate into the ground. So you don't need to put operatives down a hole, in a shored hole, hopefully it's shored, risking their lives through potential collapse. You therefore don't have to pay for all the muckaway costs either. They've not got to go, and you've not got to import concrete. So you can imagine the benefit on that carbon footprint that you've got just in what you've done there. Speed of installation as well, obviously, is a big thing. So you save on labour too. But because we've engineered this, we actually design it, we can get a defects warranty on it as well. So we have our own 10-year defects warranty guarantee that goes with that. Economical? Yeah, it's economical in the right conditions. Like every sort of solution to something, it has an economy to it. It's not cheap as chips, I can tell you that. Remember those two grouts that we were looking at? The white grout is probably about 70 pence a litre mixed and ready to deliver or ready to inject. The Geotech LV polymer is £7 a litre. Okay, so a huge difference. So if you could use the cementitious grout, wow, would you save a lot of money? But of course, you can see it doesn't work. So in fact, you use this very effectively, no more than you need to. So how much do you need? We've worked out over time and testing that it's somewhere between 7.5 and 10 litres of resin per half metre of lance. So 15 to 20 litres per metre of lance. That's all we put in, and that will give you a 0.5 metre diameter pile. Okay, this has all been worked out, one, from experimentation, two, if you think about it, soils, so we're going back to geotechnical hat on here, soils have a void ratio probably never less than 30%. never much higher than 36, 37%. And that really means that they've got a volume of about 30% air or water between the particles. So if we fill those.
Sorry, David, can I ask a question?
Yeah, you can.
So that half-meter width, is it half-meter by half-meter?
It's a round. It's a complete diameter.
So we're digging 1 meter. So it's a cylinder of 1/2 meter by 1 meter depth.
No, as deep as you want it.
I'm just trying to get into the cost. If it's going to be cheaper to use rather than using just a normal trench and.
Oh, I see what you mean. Yes. Okay, I can talk about prices. We have standard prices, and we charge. I've got to try and think now. I think it's £450 per meter of lance injected. So if you did a 2 meter pile, it will be £1,000, £900.
Thanks, David. If you can continue, if I can ask attendees to wait for questions at the end, and if you've got any questions that you would think you might forget, add them into the chat box, please. I'm sure lots of people want to ask questions. Thanks, David.
Not at all. Thanks, John. But actually not a bad question, because we were talking about the economics of it. So in fact, it's not cheap. But of course, if you can underpin a house in a few days without disturbing and sending the clients away, out of the house, all the other bits and pieces, then it becomes suddenly very cost effective and minimal disruption and reliable. And I'll show you how reliable it is. So because we're only going to use a road breaker to install these lances at a very small pump, the pump is literally about that big. It looks like a spray pump, electric spray pump, very quiet. So we can nip in anywhere. So in fact, I mean, that's an illustration of us injecting a slab through under a stairs, and we have done that. We've done it under floors. So you can be very good. We've done it in kitchens. So we've actually taken kitchen unit work surface off. We know we've obviously investigated what's behind it. We've gone in through the cupboard, we've drilled through the back, we found the footing, and we've actually injected it without even taking the kitchen units out. So it can be incredibly nimble. And as far as we know, this is the only fully designed, guaranteed ground permeation system for underpinning, anchoring, jacking, and ground consolidation, and it's patented. So we've got a worldwide patent on this. And we've been installing it for 18 years, all around the country. I haven't done it abroad enough yet. That's something we're working on. So we talked about underpinning. We want to just briefly talk about the anchoring. Now, do you remember me showing you that that pile hanging from the lance on that engine crane? Well, that's the material just hanging off it. I asked Simon during our experimentation, because we were looking early days to find out what sort of strength we were getting out of this material. No point in putting this expensive resin in the ground if we're not going to get any benefit out of it. So I asked him if he would do some strength test, classic compression strength test. So the good old 6-inch cube molds, steel cube molds, oiled up. We created the composite in there, let it cure, and then Simon had to take a sledgehammer to smash them apart, because this material, this composite, has bonded through the shuttering oil onto the steel, and we can't get it off. So we actually have to grind the surface clean. So there's a huge amount of adhesion. So we tried really thick engine grease, for joints and bearings. Exactly the same thing happened again. So in fact, we actually, to create these cubes for testing, we actually have to use cling film. That works fine. So we've tested garden soil, sands and gravels, peats, glass beads, anything permeable. Consolidated it, tested it, and we get, for this material here, which I'm going to slosh around a bit, that has a conservative compressive, unconfined compressive strength of about 3.5 to 5 newtons per millimeter squared. For those of you who deal with buildings and materials and things like that, that's about the same as a medium dense concrete block. Okay, so it's not hugely strong, but it doesn't need to be. Does anybody know what strength? Is a rhetorical question because I know you're not going to answer back. How much strength you need in the ground, compressive strength, to support a 2-story house? 0.25 of a newton per millimeter squared. Okay, that's 3.5. So that's 15 times stronger than you need it to be to support the house. So if it didn't have any of that, I mean, that material, if you took it out and crushed it without the resin in it, would have 0 compressive strength. Because remember, in the ground, it's confined, not unconfined. It's confined. In other words, to compress it, you've got to actually push all the particles together or push them away out from under the footing. So you don't need an awful lot of substance to that material to support it. Anyway, so we did that, and then I said to Simon, "That's interesting from that result. Get a Travis Perkins black bucket and do the same thing. Put our material around that lance in the bucket. Keep a lid on it. Make sure you sort of compress it so that the resin doesn't just foam, and then push that push the lance out of the material. Try and see what sort of bond strength that we've got to the lance." So he did. Remember, he's a materials engineer, so he's done lots of experimentations with presses and crushing things and you name it. Anyway, he came back. He said, "You're not going to believe this, Dave." He said, "I've just got the results back. I have, from a 300 mil length of this material, the bond strength of that is 2.75 tons." Right? I mean, just ridiculous. So I said, "That's not right." So he went back and he did it again and again and again, and we got the same results each time. To unprepared steel, this material bonds to it. So what if we turned that into stainless steel and we drove it into the ground at an angle through a retaining wall, and we injected an area of ground? You'd have one massive anchor block to pull out, and it needs to be stainless steel because you've got to rely on that not corroding. So we did, and we have, and it's worked really well. We've also used these piles for jacking loads off, so you can mechanically jack loads off them. You've got this sitting out the top of the composite material. We've got heads that you put on that, and you can actually jack slabs back into position, and then put a cheap cementitious grout underneath it to do it. And ground consolidation. Now, this is really interesting. For those of you who deal particularly with party walls and temporary works, basements are a bit of a nightmare. So we'll come on to how we do that in a minute. We have a spreadsheet, very simple geotechnical expression, and all we need from a site investigation is the type of soil we've got. So we'll have it graded so we can see what's in it, and the density, which you actually get from your site investigation. So as you're carrying out your borehole, you thump, not unlike that, actually, into the ground, an SPT cone, and it gives you a feedback of resistance and density. Okay, it's called the SPT end value. And from that, we can design those piles and get the capacity from them. Very, very simple. So here's some examples. Actually, funnily enough, we're working on this at the moment. So this is on sands up at Southwold. You probably know that Southwold sits on a lot of sand. And they're trying to redevelop it. So they've got new loads going in to areas they know they've got washout and settlement problems. And so we've put together a scheme like so to take these additional loads that they want. Very simple, just really just to illustrate how we record things onto a drawing so that our guys can see what's going on. We mark what we're going to do on the borehole logs, again, so that everybody can see what it is that we're going to do. And the technicians also have a feedback on how deep they're supposed to go and what type of material they're supposed to be finding. We do sectional drawings if necessary, so that we can also see what we're going to go through. You probably noticed that one, you're going in at a slight angle, therefore you do have an eccentricity under the footing, but remember how big this thing is, and it won't be exactly like that. You will center it. It will never be a problem. So let's look at all the different types of things that we can use it for. Solution feature. We were called in by a well-known housing company. They'd been doing some vibro compaction on a site in Maidenhead, alluvium over chalk, and we all know with chalk, solution features can be a problem because they're obviously blocked or clogged with alluvium, and then what happens is either vibration, water, or a combination, as we had it here, knocked that plug out, it drops down, and any building sitting on the top of it, or a bus or a car or a skip, suddenly disappears down the hole, and you've got yourself a lot of damage. This is what happened here. So we probed it. We got card geotechnics to come in, do probes inside and outside the building, see if we could actually find the shape of this solution feature, and that's what we found. It looks a bit like a molar, and this is some of the sort of results we were getting. So we then designed a ReFORCE system, or in fact it was GeoForce in this particular case, because we're going down a bit deeper, we used almost like scaffold tube size tubes, exactly the same technique, but we use a slightly bigger tube, and we then matched the loadings from the various walls and depths to create the support that this poor old priory needed. So that's the sort of damage that occurred. It had a basement, and that basement really was incredibly badly cracked up. Basement sat right over the solution feature. So that was the temporary work situation when we went to site. We did all that work by piling. We even tried to do filling of the solution feature with a cementitious grout. It was something that the client asked us to do. If we could fill it, would we try it? We said, well, the danger is we don't know what any fluid is going into. If we get immediate feedback and the pump starts to work harder, we know we've started to fill it. We got about 20 cubic meters of grout in there and nothing happened. So we weren't going to continue because, again, you don't know where it's going. It might be going through into a drain, deep drain somewhere. And we completed the job, and then used our structural repair techniques to put this old priory back together. And you can probably see some of the lines that are there. Normally we would colour match the mortar using lime mortars. We can colour match those so that you can't really see where it is. The conservation officer here wanted us to use natural lime, so they show up, but they'll tone down after a while. Having done that, we were then asked to look at another solution feature not far away, up in Lane End in Buckinghamshire, where a diverted stream, underground stream, had suddenly taken a plug out of a solution feature right on the flank wall of an old cottage. It had a basement, and when you went into that basement, the whole boiler had literally dropped. It was hanging by the pipes into this solution feature. Very difficult to do what we did at Boyne Hill here. And what we really wanted to do was cap it. So in fact, you use these lances at an angle to create a reinforced concrete, a bit like an umbrella, a reinforced concrete set of consolidated piles onto which you then put a reinforced concrete slab and then dry pack to the footing, and you've then capped it off, and you don't need to worry that there's actually a solution feature beneath it. So again, very successful. But we talked about this earlier on. These are all firing that into the ground and then pumping resin into it. How do we know it's worked? Yes, we've dug some of them out. But we then were called by a company called Abbey Pinfords. You all have probably heard of Abbey Pinfords. Great company, worked very closely with them over many years. And they used to be fellow ASSOC members with us. And we did different things. We obviously did this, we did traditional underpinning. They did a lot of basements. And they came to us one day and said, look, Dave, got a problem. We're working on a property in Ennismore Gardens, which is in Knightsbridge, not far from Imperial College. A fairly wealthy chap, as you can imagine, who would need to be to buy a 6-story building, because I think it's 7 actually, because it's got a mansard and a basement. And he wants to build a 2-story basement beneath that house. And for those of you who get involved in geotechnics, you'll know that at any time you do any underpinning beneath a wall, you will get some settlement or other. And that causes massive problems when it comes down to litigation, damage repair and all the other bits and pieces. So Abbey Pinford wanted to work with us to see how they could limit the potential for party wall damage. And we went down, looked at it, saw that we had terrace river gravels over London clay. Terrace river gravels are very like, you remember that jar you saw on the right hand side where we did the experimentation with permeation. That's really what they look like. In fact, that's what that is. That's terrace river gravels. So they had those over the London clay. The basement, 2-story level basement beneath the existing one, had to be dug down onto the London clay. Once you're on the London clay, that's absolutely fine. But 2.4 meters above that, in the terrace river gravels, was the water table. Now, if you try, I don't know if anybody has tried digging. It's a bit like at the beach. If you start digging a hole and the tide's fairly about, you'll see the water actually pulls the sand in, and that's exactly what happens if you try and dig in waterborne terrace river gravels or sands or anything like that. So you have to try and hold them back, otherwise you wash the fines out, down goes the party wall. So we looked at it and we said, we think we know what to do with this. We checked all the levels where the London clay was, we had extra site investigation done, and we put together a scheme. We priced it, and it's a long story, but I was quizzed on a Friday night at a rather a nice apartment in the Dorchester Hotel by a Russian and the whole of the project team. And I had to sit in a black chair under a spotlight by the fireplace, and I was grilled about my submission. And the first chap came up and he said, we think you're too expensive. So I said, that's fine. I don't mind. Not a problem. See you guys. I'm quite happy to get home for a gin and tonic. And I started to walk out. At that point, out of a cloud of smoke came a 6'4" Russian. And he said, Mr. Kitching, please sit down. I want to know more about what it is that you're offering. So I said, oh, that's great. Thank you very much indeed. But I won't sit down if that's all right. I want to stroll about because I feel much happier strolling about. I said, I want you all to imagine you're now in the ground and the water table is up by the cornice in this room. Okay, now I want you to dig down to the floor in that and be happy that you're not going to cause danger to the guys doing it, fines washing in and causing settlement. And you just tell me you thought I'd overpriced it. So this is how it is. And basically at the end of it, he just said, yeah, you got the job. Yeah, crack on. Brilliant. So off we went and we designed this. So if you look on the left there, we and the party wall and those that deal with party walls will come up with this question in a minute. I'm sure at the end, but you're putting material over the party wall line and that's usually not allowed. Well, so far, we've not had an objection to it. We've always brought it up, showed them what happens, showed them the sort of material it provides, you get, and they're absolutely happy. So we allowed Abbey Pinfords to dig down one level of basement beneath the existing basement, create their RC shell, put some blinding in, and then we cored down through the RC toe of that underpinning at different angles. You can see they're coming out at different angles there, specifically to create enough of a volume of material, of this consolidated material, to hold back the water and be safe bearing capacity wise. So that's what we did. And you can see the little group on the right hand side there, those little group in blue of the lances as we've injected them. They were cored specifically at the right angle so that when we drove, we knew we'd got them in. Each lance is a specific length, and therefore we put a specific amount of resin into each lance because one's longer than the other. Okay, we probably didn't get any into the London clay, but that didn't matter. We wanted just to make sure that we're permeating that junction between the Terrace River gravels and the London clay. Now, what that actually meant was when we completed and we'd gone round 3 sides because the London clay came up to the top level for the nib, so we only need to do 3 sides, was that Abbey Pinford's underpinning guys could simply go under their footing, trim their footing off, and then dig down and gently just break off our material. Remember, it's only about 3.5 to 5 newtons per millimeter squared. So actually it breaks quite nicely with a breaker, and they could trim it back and it just stayed there because you've also got this in it at very close centers, which act as reinforcement. So in fact, the temporary works engineers were very happy with this method. It was safe and it held back the water because this is a closed cell polymer, which means you don't get water coming through it. So as long as you get that continuity through the ground as you've done it, you will end up with a back shutter in essence. And that's exactly what they did. They finished 3 months ahead of schedule and saved the client a fortune. They also gave the client a much bigger basement because if he'd had to go for secant piling, which is the norm when you've got this sort of problem, then he'd have had secant piles inside the party wall line and then a structural liner inside that too. So in fact, he's got a much bigger basement for his money. So £250,000 as it was even 10 years ago, saved him an awful lot of money. So we know, because we've seen it excavated, how reliable it is. Here's another one. London again, Terrace River gravels again, completely different scheme this time. Behind the Dorchester Hotel, they wanted to create the Dorchester apartments, serviced apartments. So presumably they bought a building, knocked it down, and a company called Erith brought us in to say they've got a problem. Right next to the back of their site is this building here, which is a 7-story listed building just off Park Lane. And it sits on about 1 metre of concrete footing on top of the Terrace River gravels. Terrace River gravels are very good for bearing if they're not exposed. But what they needed to do the basement was a whole series of piles with a pile cap on the top. That pile cap was going to be 1 meter or 1.2 meters below the footing level, the bottom of the footing level of next door. And obviously being listed, settlement, cracks, all the bits and pieces that go without, you know, the sort of damages that you would incur are a nightmare. So they asked us to come up with a scheme. So we designed it, as you see on the left there, to create this strong layer about 2.5 meters deep, onto which their footing would sit, and it would then take any load down beyond the area for the capping beam. But what we did say to them was, look, you can't just drag it all out. We want you to do it in 2.5 meter lengths on a hit and miss basis, because this is temporary works. This stuff has a strength to it, but not in particularly in an unconfined situation, which you're going to have here when you expose it. So they started and they did the capping beam constructed in 2.5 meter lengths until the end of our first week. And we came in on the Monday morning, and a very helpful machine driver, Earthworks machine driver, had decided to get his RC team a bit ahead of schedule, and he pulled 15 meters out to over 1 meter depth all the way along the side of that building. So there's 7 stories of listed building sitting on Terrace River gravels exposed. We all panicked. We got them to backfill as soon as we could and compact it. The monitoring showed not 1 single millimeter of movement. So in fact, that material had held up, unconfined, that building. So again, what we're showing you is we do this blind, but actually we've got a lot of faith in how it delivers. So again, a very happy client. We've even done this for Balfour Beatty. And we'd consolidated some fills on a site up in Edgbaston. This is it here. And that building was going to be turned into sort of like a administration and activity centre, I think, for sort of supported sheltered housing of some sort. Anyway, they needed to build beside that flank walls you see there, a 3.5 meter deep plant room, RC walled plant room. But they didn't know how they were going to go down. If they'd put piles in, they'd have shaken it to pieces. And so what they decided to do was ask us to come in and consolidate the material under there to support the building so that they can then excavate out. We looked at the soils and said, no, we're not happy. We've done your fills, they're all right, but the material is very fine, silty, almost cemented sand. But they said, okay, we'll pay you to do a trial. So we did a trial. I wasn't even happy with the results of that, but they said, we think it's good enough for you to crack on. So we did. We actually went and designed and installed an underpinning thing like that, and they managed to do it. So again, we've seen it. Even Balfour Beatty have approved that. How are we doing for time, guys? We're bang on 5:30. You'll probably want to get down to the pub.
If you could close up in 5 minutes, that'd be great, David. Thank you.
Right. Well, I'm going to show you here something really, really interesting, completely different. It brings in one of the other things that we do, and I'll try and keep it to 5 minutes.
Sorry, Mr. Littlewood, can I ask a question?
Yeah, you can.
So in terms of the 7-story in Park Lane...
Sorry, can I ask you to leave your questions and let David close up, and then you can answer your question.
Sorry.
Okay, no problem.
Thank you.
So here we are. This is a historic bridge, designed and built by Brunel on the east-west line, just west of Reading. When we were called in by Network Rail, using our Goldhawk, putting our Goldhawk hats on, we found that arch was bouncing over 10 millimeters when a freight train went over it. Now you can't believe that the center of that arch actually was bouncing like this. I'd never seen anything like it. It was like a ferret in a bag when you saw it. Brickwork rippled as a train went over. So we were asked, could we strengthen it using our Mars system? The answer was yes, we can strengthen it, but no, we can't take that amount of bounce out of it, because the whole idea of the Mars system is it keeps arches flexible, and that's how they transmit their load around them. That's why they work, because they're not rigid. But we said we got an idea, and we gave them Network Rail this lecture that you've just had, and they said, like it, go for it. So that's a dynamic monitor of the unaffected arch, and we designed the ReFORCE system. You'll see a similarity there between that and the Ennismore Gardens job with the radial lances. The Mars system on the left, that's for another thing, but that's how we strengthen the arch. So what we wanted to do was increase the stiffness of the fill that sat either side of the haunches or either side of the crown. Because what happens is when that crown drops, the haunches move out. The actual shape of the arch changes. So if you can stiffen that, you will immediately stiffen the deflection in the arches. So we did. They gave us the commission. That's the Mars system. And in we went. We actually put propping in. We never normally put propping in, but because that brickwork was so lively, we didn't have any choice to safeguard our workforce. So we actually put props in, but they've got a 25mm neoprene rubber gasket on it that allowed the arch to flex. So we're not creating any hard spots so that you wouldn't get fracturing happening. And in we went, and we installed the lances and injected them, all different lengths, exactly the right amount of resin. Okay. Network Rail are paranoid about you leaking resin into their track bed, lifting their track, you know, with this expansion of resin that other contractors do, and obviously they've had massive problems with. They realized that we didn't do that because we permeate it, it takes up the spaces between the particles and stops. That's it, doesn't move any particles. So actually we put 4 cubic meters of liquid resin into the ground. Okay, so that then expands 2.6 times in the sort of areas or the confinement that we've got there. So there's then probably about 11 cubic meters of resin, but that only takes up 30% of the volume of the soil. So increase that, you have actually consolidated completely width to width a huge volume of soil or fill. Oh, by the way, we had that tested, and it was sand, so we knew we could permeate it. And immediately we took 2/3 of the bounce of that arch out, which meant we had a pretty good chance to put our Mars system in. This is the Mars system, which wish we can do another time. That's how we put it in. And when we completed it, that was the level of movement in the arch. So we'd taken it from what we measured as 11, dynamic monitoring measured it as 6, down to just over 1. And that's what it looks like at the end of the day. So Network Rail are absolutely delighted because they didn't have to take a single train out of timetable. Obviously that saves them an absolute fortune, and we completed it on time and on budget. So, questions?
David, I'd just like to say thank you very much on behalf of Chartered Association of Building Engineers Wales Committee for your wonderful presentation. And we don't have any questions, I don't think, in the chat box, so I'll open up the floor to anyone who's got any questions. If you could say your name and who you represent today, that would be great. So anyone who would like to ask a question, please go ahead.
Thanks, John.
David, in terms of the 7-story in...
Sorry, could you tell us, give your name and who you represent today? You might have missed that as you popped out of the room.
My name is Sajad. I represent myself. I've got my own structural engineering firm. We've designed the tower to replace the Grenfell Memorial.
Ah, wow.
Yeah, so in terms of power foundations, it's going to be a lot more lucrative because it's going to be more cost effective, less use of staff, and in terms of the strength, it's incredible. It's beyond what I thought it was 7.2 kilonewtons for a footing, but it turns out it's 3.6. So that means I've been over designing it all these years.
It is surprising, isn't it, just how little strength you need from the ground to support something. What's important is you know, if you want us to have a look at that at any time, would be the site investigation. That is critical. If we can't permeate it, you can't do it. So a lot of other companies at the moment, we're talking about soils, you can and can't inject, you cannot inject clay. And no matter who tells you can, you can't. Take my word for it.
So then your call out would be how much if we could
Call out. Oh, we'll
to Grenfell, to the site of the fire.
Well, nothing. We're just down the road.
Oh, brilliant.
So, but what we'd ask you to do is send us information first. So it might be a wasted journey. So we want to see what it is you're doing, what the soils are, and we will then actually work out whether what you hope might work will. See what I mean? First, before we go to site.
So David, it's David at permeationengineering.com.
So it is David.Kitching, Kitching at stressuk.com.
Might be helpful, David, if you put that into the chat box for other people, because it'll be picked up on the recording as well.
I'm just doing that now, guys. So you've got that.
Matt will do that for us.
Brilliant. Thank you very much, Matt.
No, that'll be very interesting to have a look at that. See if there's anything we can help with.
Sajid, do you have any further questions?
Thank you very much, John. Thank you.
No problem. We've got a question in the chat box from Muna Alama. Can this technology replace the pile system? And when injecting the grout material, when do you stop the injection?
Good questions too. Let's go back to the economics of this. So if you had an open site where you could track a piled rig onto and use a cementitious pile, it's going to be an awful lot cheaper. If you had a site, however, that you couldn't get to because there's another building there, or a quadrangle, you need to put something in a quadrangle, unless you get a very, very large crane and lift the piling rig right over the top and drop it into the quadrangle, then our system might be more cost effective and quicker. What was the second part?
The second part was when injecting the grout material, when do you stop the injection?
Remember, we know exactly how much we need to create a half-meter pile. So it's between 15 and 20 litres of resin per metre of lance. So it was a 2-metre lance, we'd put 40 litres of resin in. We don't put any more, we don't put any less. That's what we put in. So we can give you a fixed price. Very straightforward.
Thank you, David. Muna's actually got her hand up. Did you want to ask any further questions, Muna? You're on mute at the moment. Unfortunately, we can't hear you. Do you want to type your question into the chat box? That might help. While Muna's doing that, does anyone else have any questions? Oh, thank you. Yeah. Thank you here from Alan G. No more questions from Muna. Okay. Does anyone else who's attending today have any further questions for David? What I would like everyone to do is just give an example of which professional body you represent. If you could put that into the chat box, it would be great, helpful for us at CABE, and where you are located in the world. That also would be great, very helpful, not just to CABE, but also to David and Matt who are presenting. That'd be really helpful.
Actually, yeah, that'd be great.
Particularly in the context of what you started with, you know, you said that the company and group are doing some work internationally, but you know, you'd like to do a lot more. I think we've got quite a few international representatives here today.
Well, that, as I say, is very interesting, because we can we can take this anywhere in the world, you know, under the right circumstances. So yeah, it's something that, do you know what, we just don't have time to do. We're too busy doing other things. So finding the opportunity, I should be at my age, I should be slowing down or retiring, but I'm doing more and more of this. So Matt's got me presenting most of the time, and I leave the running of the company to the younger
generation.
Yeah, they're doing a great job.
Now, Rosemary does have a list of people who have attended, as I'm sure she can share with you where those people are located, which would be helpful for yourselves.
That would be very good indeed. That would be great.
Okay,
well, I very much enjoyed it, John.
Brilliant. Thank you. Yeah.
You've been a very buoyant audience, I think is probably the best way of putting it.
Brilliant. Thank you very much. And thank you for everybody who's attended today. Thanks to KBHQ for hosting the teams, and as part of Wales committee and our other committee members, thanks very much for attending. Hope you found it useful, and that you'll take forward the suggestions put forward by David. So we've got quite a few people here. We've got Brixton Devon. We've got Brixton Devon Building Engineer, Devon Building Engineers, Morgan Wolf Limited Approved Inspectors, Log Creation Quadrant Approved Inspectors. That's reading from the chat box from Liverpool. Yeah, there. Thanks very much, everybody. I hope you have a good evening. Beauty of CPD Online. Hopefully you're now safe at home, or if not, hopefully you'll have a safe journey home. Thanks very much, everybody.
Thank you,
evening.
John. Lovely to see you. Take care and all the best.